In this video lecture, we'll look at destabilization caused by feedback. So far in this chapter, we've been only talking about the benefits of feedback, and there are many applications where feedback is beneficial. However, unintentional feedback may also cause undesirable effects, such as causing a stable system to become unstable. A few examples of that, one is a tracking system that has a gain that's too large may produce what's called overshoot and ringing of the output instead of settling right onto the set point. Another example that you can actually do at home is with the inverted pendulum that we talked about in the last lecture. So in the last lecture, we talked about how you can take an unstable system like a stick that's balancing in your hand. And if you just keep your hand still, the stick will fall down because it's unstable. But we saw that by making little adjustments with coordination between your eyes and your hand movements, you can actually balance the stick. And this is something you should try at home. Use a long stick like a broom handle or something. It's a little bit easier. However, if the gain of the system here is too large, in other words, every time you make an adjustment with your hand, if you push your hand back and forth too much, then the system becomes unstable again. So in this case, too much feedback is not a good thing. The example that we're going to focus on in this video is another one that's probably familiar to you, and that is the example of unwanted feedback with an audio system, which happens when the speaker and the microphone get too close together. So I can do a quick demo of this. You'll be able to listen to this. I've got a microphone attached to a speaker on an amplifier. So let's see, you should be able to hear my voice amplified right now. And now I'm going to bring the microphone closer to the speaker. And we get some very unpleasant sounds coming out of the system. All right, I'll turn that off. Thank goodness. So let's take a look at the audio feedback problem in a little more detail. So here's a sort of a block diagram, if you will, of showing the system. We've got an amplifier here, which the output of the amplifier is connected to a speaker, and the input of the amplifier is connected to the microphone here. And so as we just demonstrated, if the microphone gets too close to the speaker, what happens here is the microphone picks up the sound from the speaker, returns it to the amplifier, which amplifies the sound, and then the speaker sends that sound right back to the microphone, and we've got a feedback loop here with unwanted positive feedback, and this just builds up over time until it produces that horrible loud squealing sound. So here's how we can model this system rather effectively. You notice this is a standard feedback loop system here with linear feedback. So over here on the left, we've got external audio inputs. So this X of t here would be sounds going into our microphone, such as voice or music or something like that. Now, this is the signal coming from the microphone, basically going into the amplifier. So what we're going to do here, just to make things as simple as possible, we will model the amplifier as if it just has a constant gain, which we'll call K1. So K1 is our amplifier gain. And for a typical audio amplifier, like a PA system, think about in a sports stadium or something like that, this is going to be a very large gain. The amplifier is going to have a gain much larger than 1. So then the amplifier sends its signal to the speaker, right? That's represented by this wire here or this line here in our diagram. So Y here, Y of t, is our speaker output. Now, the feedback comes from, again, it comes from the speaker sound reaching the microphone and going back into the system. So we can represent that by taking a feedback from the output here, our Y of t, and sending it into a subsystem which models the room or the arena, let's say, if this is a PA system. So how do we model the room? Well, the room does two things. The room has a gain, which is actually not a gain, it's a loss called attenuation. And that's due to the fact that the sound has to travel around and spread out throughout the room. So we'll call the gain of the room K2, which is going to certainly be less than 1. The farther you are away from the speaker, the softer the sound. So that's modeled by K2. The room does something else though. There's also a delay. There's a propagation delay. It takes time for the sound to get from the speaker to the microphone because the sound travels at the speed of sound. So we'll call uppercase T our propagation delay due to the distance between the speaker and the microphone. And that, of course, is equal to the distance, D, divided by V sub S, which is speed of sound. So in the time domain, we have Y of T going into the room. And what the room does to that sound signal is it attenuates it, multiplies it by K2, which reduces the sound, and then it delays it. So we have Y of T minus uppercase T, which is our propagation delay. To find out what the transfer function of this would be, it's actually not that difficult. Remember the time shifting property from chapter 9. If we have a signal Y whose Laplace transform is big Y of S, then if we delay Y by some amount uppercase T, our prop delay, then that delay is taken care of by a factor of e to the minus st, where t, again, this is the uppercase T, which is the propagation delay. So with all that said, we can model both the attenuation and the delay of the room as a subsystem that has a response given by K2 times e to the minus st. So K2, again, is the attenuation, and e to the minus st takes care of the delay. So this is our model of the room or the environment in which the speaker and the microphone are placed. Now that we have a model for our audio system, we can take a look at the condition for stability of this audio system that has the unwanted feedback. Before I forget, I didn't mention in the last slide that one thing that's different about this feedback system compared to others that we've looked at so far in this chapter is notice the plus sign right here. This is because this is an example of positive feedback. Positive feedback in general is going to cause instability because it's going to keep growing and growing instead of subtracting away. So we'll see that when we do the system algebra shortly. But here is our total system here that we described and built in the last slide. Remember, this is our amplifier, our audio amplifier, which is just represented by the gain K1. And then our feedback loop has the room in it, which is represented by the attenuation K2 and the delay e to the minus st. That's the propagation delay. So we can go ahead and perform our system algebra. It's always easiest to do it right on the block diagram. So here's our output Y. So Y goes into the room here, and all we have to do is multiply Y times the transfer function of the room. So we get K2 times e to the minus st times Y coming out of the room and going back into the microphone here. So we're adding that to any intentional sounds that are coming into the microphone. For example, X here could be the speaker who's not the person talking into the microphone, or it could be music or something like that. But anyway, we're going to add X to our K2 e to the minus sty, which is the signal coming out of the room here, and that all goes into the amplifier. So this is the total signal that the microphone picks up and feeds into the amplifier. Now, the audio amplifier, remember, all it does in our simple model here is multiply this signal by the gain, K1. So we just take this expression here on the left coming in, and we multiply it by K1. So I've done that here. So this expression on the output here, K1 times the quantity X plus K2 e to the minus st times Y, is equal to the speaker output Y. So I've copied that exact equation right here. And from here, we can figure out the overall transfer function of this whole system, including the room. Remember that the feedback system transfer function, we typically call Q of S, and that's equal to the output Y of S over the input X of S. So from this expression up here, we can just do a little algebra. I don't show the steps, but it's pretty simple. You can distribute this K1 inside the parentheses here. And then this term over here has a y in it. So that's moved to the left side. And we can factor out the y and leaving K1x on the right side. And finally, we can do the division. I didn't show the steps here because we've done this many times in the previous videos. But you can easily verify that the resulting transfer function is equal to K1 over 1 minus K1, K2 times e to the minus st. So let's find the pole of this transfer function. Remember, to find the pole of a transfer function, you just have to set the denominator to 0 because the pole is a root of the denominator. So the condition where the pole, to find the pole, is that K1, K2, e to the minus st is equal to 1. And I put the little naught there, S naught, which indicates that S naught is our pole. So we can solve this for S naught. So to do this, let's move the K1 and K2 to the other side. So I've got e to the minus st equals K1, K2, all to the negative 1 power, all right, because we divided by K1, K2. Then to solve for S, we just have to take the natural log, so we get minus S naught t equals natural log of this term here, K1, K2 to the minus 1. And we can use our properties of logarithms, that minus 1 in the exponent here, we can bring that out to the front, which just becomes a minus sign. So now this minus sign cancels with this minus sign, which is nice. And finally, to solve for S naught, we can just divide everything over here on the right by uppercase T. So here's our, after we solve for S naught, here is our pole. Our pole, S naught, is equal to 1 over T, remember T is the propagation delay, times the natural log of K1 and K2. So recall from chapter 9 that for a causal system, a system is stable if and only if the poles are in the left half plane. So in order for this pole to be in the left half plane, we need it to be negative, because notice this is a real pole. It's a real number. These are all real numbers. T, K1, and K2 are real numbers. So how does this become negative? Well, a logarithm becomes negative when the argument of the logarithm is less than 1. Okay, so in other words, to get natural log of K1, K2 less than 0, we need K1 times K2 to be less than 1. So this is our audio system stability criterion. We need the product of the two gains, the amplifier and the room, each have their own gain. We need their total product to be less than 1. This is called the loop gain, which is the total gain when we go around the loop here. So what happens here, if the gain of the whole system, K1 times K2, is greater than or equal to 1, then our pole here is positive, meaning it's moved to the right half plane. The system has now become unstable, and what happens is we're going to end up with resonant frequency output with a growing amplitude, and that's the squealing sound that we've heard in the demo. And we'll take a look at how we can actually predict and model that behavior on the next slide. So we just determined that the audio system becomes unstable if the total gain of the system, that was K1 times K2, is greater than 1. And conceptually that makes sense, because if the total gain is greater than 1, then that means each time this signal goes around the loop, it gets louder because the gain is increasing. On the other hand, if K1 times K2 is less than 1, then each time around the loop, the signal is going to decrease, and basically it'll just attenuate and decay to 0. And that's what we want. That's for a stable audio system. But let's take a look at what happens when we get an instability and we get that unwanted audio feedback. So our goal here is to determine the system output, y of t, when we're operating in the unstable feedback region. So to make things simple here, our method is we're going to just let the input to our system be a delta function. All right, so this is just, you can think of the delta function here as just sort of something to sort of kickstart the system, to give it a little bit of audio input and get this thing rocking basically with the audio feedback. So recall that the system impulse response, h of t, is the inverse transform of the system function, or the transfer function, h of s. Now, the other thing we're going to do, again, just to keep things as simple as possible here, let's assume that our loop gain, k1 times k2, is exactly equal to 1. All right, and this is also, this leads to instability. It doesn't lead to a growing amplitude, but it leads to an instability, which is what we want to model here. So let's start here with our transfer function. So we derived this on the last couple of slides. H of s was equal to k1, that was the audio amplifier gain, divided by 1 minus k1 k2 times e to the minus st. So I'm going to take this k1 on the top here and bring it out in front and put everything else in parentheses. Now remember, we're setting the product k1, k2, which is our loop gain, we're setting it equal to 1. So that's why it disappears here in this term right here. Now, this expression inside the parentheses here, we can use a trick here. This looks familiar. If you recall the infinite sum formula, whenever we have a sum from n equals 0 to infinity of some number alpha to the n, as long as alpha is less than 1, we have 1 over 1 minus alpha. So this is a convergent series here. So what we can do here is, if we compare these two expressions here, we see that alpha is just e to the minus st. So I can replace this term in the parentheses with an infinite sum from n equals 0 to infinity of e to the minus st, that's our alpha, to the nth power. So we end up with an infinite series. K1, remember, is out in front. So when n is 0, we get this term to the 0 power, which always just gives us 1. When n is 1, we get e to the minus st. When n is 2, we get e to the minus s2t, and so on and so on. All right, so from here, we can actually do the inverse Laplace transform pretty much by inspection. So remember that the inverse Laplace transform of 1 just gives us a delta function, right? Because a delta function has a transform equal to 1. When we see e to the minus st, we can use the time shifting property. The time shifting property says that if we have a signal that's delayed by t naught, then we pick up a factor of e to the minus s t naught. So all this means here, this e to the minus st, this is a delta function that has been delayed by the propagation delay, uppercase T. Likewise, this term here, notice, is delayed by 2t, because if we compare this term here with this here, we see that we get a delta function, which is delayed by 2 times the prop delay. So what we found here is that for the delta function input, we get an impulse response, h of t, equal to k1, which is just the amplifier gain, times all this stuff inside the square brackets here is a periodic impulse train with period t. So this is plotted here. So in other words, we have an impulse, delta t, at time 0, and its weight is k1. We have another delta function at time t, all right, which is our propagation delay due to the speed of sound. And then we have another one at 2t and another one at 3t, and so on and so on. So what our output is basically it's a periodic pulse train. Now we can, this basically it's kind of makes sense here, because what's happening is we put an impulse into this system, and there's a propagation delay. It takes some time for that impulse to come out of the speaker and reach the microphone. Now, how much time does that take? Well, it takes this t right here, which is our prop delay. And then that signal is, immediately fed back into the system electronically, which comes back out the speaker, And then another prop delay, we get the impulse again. And so this thing just repeats itself. So now what is the frequency of this impulse train? Well, that's easy enough. So here our output, the frequency is 1 over the period, all right? And our period is just t right here, our prop delay. And remember from the other slide that the prop delay is the distance between the speaker and the microphone divided by the speed of sound. So at room temperature, the speed of sound is about 340 meters per second. And if we divide that by the distance between the speaker and the mic, we'll get the frequency of the unwanted squealing sound from the feedback. One thing you can notice here is that if we put the microphone closer to the speaker, we're reducing the distance. That makes the frequency here increase because the distance is down in the bottom. So one more time, I'll demonstrate. And what I'm going to do is move the microphone closer and farther away from the speaker, and you can hear the frequency of the squealing change. And that is our unwanted audio feedback. I hope you enjoyed this video.